And yep, this one is also good. Let me see, what was the problem? Okay, so let's just do problem 4 as an example, and then we can move on. Okay, so let me just copy down the data. So the reaction was unbalanced. So before you solved the problem, you actually had to balance the reaction first. So I in the answer key, I balanced it for you. So 2 moles of sodium thiosulfate plus 1 mole of silver bromide goes to 1 mole of sodium bromide plus a complex. Okay. Okay. So what was the question again? Let's see. How many moles are needed to react completely with 42.7 grams of AgBr? Okay, so 42.7. Oh, my bad. Let me get my calculator. Okay, so the first step we need to do is to determine the molar mass of silver bromide. So let's see. So on the periodic table, silver is 107.87. So 7 plus bromine. So 7, 9.9. So the molecular weight, so the molar mass, which is sometimes called molecular weight, equals 187.77. Okay. So now we need to find the total number of moles. So to do that, you can do 42.7 grams times 1. Right? So then this equals, let me see, 42.7 equals 0.227 moles. Okay? So now we need to figure out how many moles of sodium thiosulfate we need. So can someone tell me what so the ratio of thiosulfate to silver bromide is 2 to 1, right? So we need to do 0.227 times 2 moles of sodium thiosulfate divided by 1 mole of AgBr. And then this equals, so 0.455 moles. Okay? Now, so what is the mass of sodium bromide that will be produced from 42.7 grams of silver bromide? Well, we already did the hard work. So there are 0.227 moles of sodium of silver bromide, and then they're in a 1-to-1 ratio. So we're gonna make 0.227 moles of sodium bromide. So now we just need to find the molecular weight of sodium bromide. And that equals, so 23 plus 79.9. So 23 plus 79.9. So that equals 102.9. And then 102.9 grams per mole times 0.227 mole equals 23.4 grams. Okay? So I just wanted to do the first one as an example. And this time there weren't any limiting reagent problems. So if anyone wants those, I might make some. Okay? So now on to the, any questions? If not, that's great, okay? So now we can talk about the topic of today's lecture, which is going to be gases. So what is a gas? So a gas is a state of matter. So can someone tell me what the other 3 states of matter are? The fundamental states of matter? Does anyone know solid, liquid, and plasma? Yep, great. So actually, in the next lecture, I think we're going to talk about solids and liquids, but you don't really see plasmas in chemistry, so we don't need to talk about that, okay? So this is a state of matter. And in the gas phase, so this in the gaseous state of matter, so we have freely moving particles. So gases are made of particles, so in this picture, that just fly around at some high speed. So the particles, they move freely. And one important thing to know is that gases are not very dense. So you can see we have this airship. So the airships are filled with hydrogen or helium. So, and because they're so light, they float in air. And gases are made of individual atoms, so these individual atom particles, and or molecules. So here we have a sample of gaseous bromine, and bromine exists as Br2. So yep, so this is Br2. So so instead of atomic particles, we have these molecules of Br2 flying around. Okay, so this bromine happens to have a very nice color, but it's also very toxic. Okay, so one thing I want to talk about is kinetic molecular theory. So this was formulated back in like the 1800s. So this is Ludwig Boltzmann. So Mr. Boltzmann here. We have Maxwell, and I can't remember his name. But yeah, so Maxwell Boltzmann. Yeah. So this kind of provides us with a description of what we call an ideal gas. So this gas will have, well, like the name suggests, ideal behavior, perfect behavior. So it has perfect mathematical behavior. It doesn't have any like weird stuff going on, okay? So there are four main ideas with kinetic molecular theory. So the first one is that gases consists of particles in continuous random motion. So particles that are always moving, and they're moving randomly. So, and these particles can be atoms or molecules, okay? Another assumption is that the volume of these particles is negligible. So we can treat the volume of the molecules and atoms to be zero. And also, attractive and repulsive forces are negligible. So basically, the particles don't attract each other and they don't repel each other, okay? And the kinetic energy of the gas particles, so how much energy they have, translational energy, so 1/2 mv squared, so is proportional to the temperature in kelvins, so directly proportional to the temperature in kelvins, okay? So I'll give you a minute to write that down. Or you can always refer to these slides later, okay? So now we're going to talk about gas laws. So this is so gas laws are these mathematical formulas that allow us to relate the major properties of gases. So what are the major properties that we need to consider? So we need to consider pressure, so the pressure of the gas, the volume of the gas, the temperature of the gas, the number of moles of the gas. So in symbolically, you can say that pressure is just P, volume is a capital V, temperature is T, number of moles is a lowercase n, okay? So these are the major properties of gases that you need to know. And now we're gonna look at gas laws so that we can relate all of these mathematically, okay? So the first gas law that I want to talk about is Boyle's law. So Boyle's law says that the pressure times volume is a constant, so some constant. And also, So you can translate this as pressure is directly proportional to 1 over the volume. So what this suggests is that if you graph pressure versus volume at some constant temperature, so keeping all of your other properties the same and only changing pressure and volume, you should get a hyperbola. So you can see on the graph here, yep, we do get part of a hyperbola, okay? So, and what's the justification for this law? So, as the volume decreases, you have more particles confined in a given area. So where does pressure come from? The pressure comes from the particles colliding with the walls of your container. So the particles are constantly colliding with your container because they have, and so this imparts some force onto the walls of the container, which is pressure. And pressure is force divided by area. So that means when we confine more particles into a smaller area, the area gets smaller. So that means the pressure increases because force over area is increasing. So I think we could demonstrate this. So let me pull up the camera. Okay, okay, that's not the best camera. Okay, so, okay. So what I have here is a scale, a kitchen scale. So I'll turn it on. Okay. So I also have a syringe here. So a syringe filled with air. So. Okay. So what I want you to notice is that as I start to press down on the syringe and the volume decreases, you can see the weight on the scale is increasing. So that means it's exerting more force on the scale. So, yeah. So when I get down to the end of the syringe, it's starting to really increase because when I near the end of the syringe, there's only a few milliliters of gas left. So when I compress it just 1 milliliter, that might be having the volume doubling the pressure. So it requires a lot of force to push the syringe all the way to the end. So, okay. Okay. So now the next gas law that I want to talk about is Charles' law. So Charles's law, okay? So this states that volume is directly proportional to temperature, or the volume divided by the temperature is some constant. The temperature is in kelvins, so you have to use Kelvin temperature, not Celsius temperature. Can anyone remember how to convert Celsius to kelvins? Close. So you don't subtract 273.15. You need to add 273.15. So just add 273, okay? So that means, so what's interesting about this is that, okay, so let's say we graph temperature in some scale, and then we graph the volume. That when we plot this line, and then if we extrapolate this line, then we should be able to figure out what absolute zero is. So at absolute zero, theoretically, the gas would have zero volume. So ideally. And what's the justification for this? Okay. So as particles move faster, they have more energy. So, and when they collide with the wall of the container, there's more force. So in order to maintain the pressure, if you want the pressure to be a constant, then the volume has to increase, okay? The volume has to increase to make sure that the pressure is a constant. So This is the idea behind hot air balloons. So as the gas heats up, the volume increases and it becomes less dense. So that means that the balloon becomes lighter than air, so it floats. So just to demonstrate this, okay. Let me change the camera. Can everyone see how well can you see it? Is it good? Okay. So, I'm filling this plate with water. So that should be enough. So I have a candle here, and I'm going to light the candle. I'm going to try to light the candle. There we go. Let me turn on the lights. Okay. So what I'm going to do is I'm going to put this beaker on top of the candle, and let's see what happens. So as the candle consumes oxygen, it will go out. But what happens next? Can you all see the water level rising? So what's happening here is that water is getting sucked up into the beaker. So water is getting sucked into the beaker, and you can see this as the water level rising, okay? So does anyone have a guess why this happens? So based on Charles's law, does anyone have kind of an explanation for this? Okay. So the idea is that when you have a candle burning, okay, remember that temperature is directly proportional to volume. So if the temperature increases, the volume will also increase. So what happens is that at first, when I put the beaker on top of the candle, the beaker is filled with very hot air from the candle, right? Because the candle is heating the air around it and making it very hot. Then the candle runs out of oxygen. So the combustion reaction consumes oxygen. So eventually there is no more oxygen left in the beaker to support combustion. So the candle goes out. And then once the candle goes out, so all of this very hot air is in contact with the cold water. So the cold water cools the air down, and the air cools, which means the volume of the gas inside decreases. And then since the volume is decreasing, water gets sucked up into the beaker, okay? So I'm gonna try to clean this up right now. Let's do a problem now. So using this data, can you try to calculate the value of absolute zero in Celsius? So I'll give you guys a minute to try to do this. So using the data, and don't worry about the units, it doesn't matter. So how do we solve this problem? So Okay, so I've drawn a nice graph here. So on the x-axis, we have the temperature in Celsius, and on the y-axis, we have volume with some arbitrary unit, okay? So we want to find this point, the value of the x-intercept. This will tell us when the volume is 0 and when the absolute temperature is 0, okay? So how do we do this? We need to find the equation of the line, okay? So we need to find some relationship where volume equals m times temperature plus b, okay? Where m and b are constants. So can someone tell me what the value of b is? Looking at the graph. So what should b equal to? What should b equal? Great. So b is just the y-intercept. So b equals 20. Okay. So now we need to find m. So does anyone know what m is? M is the slope, right? So now we need to find the slope of this line. So the slope is going to be 27.3 minus 20 divided by 100 minus 0, which equals 0.073, okay? So now we have an equation, volume equals 0.073 T plus 20, and then we need to solve, so now we set V equals 0, and you should get T equals 274 Kelvin. So this is actually pretty close to the actual value. So that means we've done a good job, okay? So now okay. Now I want to just briefly talk about Gay-Lussac's law. So this just says that pressure is proportional to temperature, or pressure divided by temperature is a constant. I don't really have anything to say about this one, really. It's the same explanation as the previous law. Okay. Okay, now here's an important one. So this is Avogadro's law. So this is the idea that volume is directly proportional to the number of moles, okay? So if I have a sample of 1 mole of gas, and then I add another mole, so now I have 2 moles, the volume will double, okay? Now, what's very important to know about this is that the volume only depends on the moles of gas, okay? The volume does not depend on the identity of the gas, right? Okay? So if I have 2 moles, if I have a mole of oxygen gas and a mole of nitrogen gas, they have the same volume. If I have a mole of oxygen gas and a mole of argon gas, they have the same volume, okay? So assuming that the pressure and temperature are the same, the volume only depends on the number of moles of gas, not the identity. So this means that we can easily calculate the density of a gas, and we'll come back to this, okay? And finally, I want to talk about Dalton's law. So Dalton's law is the idea that if I have a lot of different constituents to a gas, then the sum of their pressures, so the pressure of all of the constituents of a mixture, is the total pressure. So let's say we have this, okay? So let's say we have a mixture of gas consisting, so we have, so the total pressure, let's just say, is 10 atmospheres, okay? And then let's say by moles, it's 5% H2, and 10% CO2, and 85% O2, okay? And let's say we want to know what the pressure of CO2 is, the partial pressure of CO2. So the partial pressure of CO2 is just 10% times 10 atmospheres, so 1/8 atmosphere, okay? And you might have noticed that I said by moles. So I want to introduce the concept of the mole fraction. Okay, the mole fraction. So the mole fraction, X, so let's say mole fraction of X sub A. So this means it's the number of moles of A, so the number of moles of A, divided by the sum of all the number of moles, the total number of moles. Okay. So as an example, let's say we have 10 moles H2O and 5 moles of ethanol. Can someone tell me what the mole fraction of ethanol is? Yeah, great. It's just 1/3. So the moles of A divided by the total, the moles of what you're considering divided by the total moles. So in this case, can someone tell me the mole fraction of CO2? So what's the mole fraction of CO2? Great, yeah, 0.1. So if we had 100 moles, let's just pretend we have 100 moles total. So then we would have 10% of 100, so it's just 10 over 100, so 0.1, okay? Okay, so now this is the important equation that you should definitely write down and memorize. So all of the gas laws that we talked about earlier are really just one gas law. We can sum all of this up in one gas law. So this gas law is called the ideal gas law. So PV equals nRT. Okay. So PV equals nRT. And then R is a constant called the ideal gas constant. And it's equal to 8.314 joules per mole Kelvin, or 0.08206 liter atmospheres per mole Kelvin. So strange units, but okay. So you need to pay attention to the units here. Very important. So depending on the problem, you'll use different values of R. And as it turns out, this constant actually appears a lot in chemistry. And the reason why, I guess you can think of, because R is actually equal to the Boltzmann constant times the Avogadro constant. So that's has kind of a deeper meaning. So you need to pay attention to the units. And just as a side note, there are some strange units of pressure out there. And one common one is the torr, so TORR, or millimeters of mercury. Okay, so 760 torr equals 1 atmosphere. So you might be wondering where this name comes from. So this comes from a little bit of history. So basically the idea is you have a barometer. So the old barometers were made from mercury. So you have a dish filled with, and then you have an inverted tube in it. Okay. And then you have some amount of mercury. Okay. So, mercury is a liquid metal. So it's a very dense liquid metal. So now, how high is this column? Okay. Well, the height of this column depends on how hard the air presses down on the dish. Okay? So the weight of the air is 1 atmosphere. So the air pushes down on the mercury with a force of with 1 atmosphere. So that means, so you can equate this height to pressure. So for example, if it's a rainy day, then the pressure of the air will decrease and the height of this column will decrease since there's not enough pressure to push the mercury all the way up. So that means that this is where the whole 760 millimeters of mercury comes from. Okay, so 1 atmosphere corresponds to a height in the tube of 760 millimeters. Okay, so that's where that comes from. Now let's do a problem. So this is an example AP problem that you might see this on the AP test. Okay, so I'll give you guys 10 minutes to read through the problem and solve it. Let's go over the problem. So a gas occupies 250 milliliters and has a pressure of 550 millimeters of mercury at 25 Celsius. Okay, so the first thing is to convert these to useful units, okay? Because we can't just plug these numbers into the gas law. So can someone tell me the volume in liters? What's the volume in liters? Okay, so we have 0.25 liters. What's the pressure in atmospheres? So remember, 1 atmosphere equals 760 millimeters of mercury. So can someone tell me the pressure in atmospheres? Anyone? Great, 0.72. So we'll say 0.724. So, yeah. So just divide by 760, okay? And can someone tell me the temperature in Kelvin? In kelvins. Great, 298. So we'll round that to 298. So since I don't think anyone actually uses 273.15, so you can just use 273. That's good enough. Okay. So the gas expands to 0.45 liters. Okay. And everything else is kept the same. So, how do I get to the camera? Okay. So there are several ways to solve this problem mathematically, but in my opinion, the easiest way is to just calculate the number of moles. So that way we have all 4 parameters and everything is nice. So how do we do N? Okay, so PV equals nRT, and we need to calculate N. So N equals PV over RT equals, so 0.724. I'm not going to include units because they all cancel out, but you should include units in your calculations. Times 0.25 liters divided by 0.08206 times 298. And this equals Okay, so that's how many moles we have. So now we have all 4 parameters, so we can change any two of, now we can change anything and we can calculate the new value. So now our new value of volume is 0.45 liters, and we want to calculate the pressure, right? Okay, so, and we keep everything else the same. So we rearrange this equation, so P equals B, and this equals 7.4 times 10 to the minus 3 times 0.08206 times 298 divided by 0.45. And what does this equal? Let me see. 0.40 ATM. Okay. By the way, when you do your problems, you should include units, but I'm not including them to save a little bit of space. Okay. So now what's the next part of the problem? What temperature is needed to increase the volume of the increase the pressure of the gas to 1 atmosphere while keeping the volume constant? Okay. So now, what temperature, right? No, what temperature? So again, we just rearrange the equation. And we want to increase the pressure to 1 atmosphere. So equals 1 times the volume divided by times 0.08206. And this equals and then to convert to Celsius, we just subtract 273. So 8 Celsius, 139 Celsius. Okay. Now let's move on to the next part of the problem. Okay, how many moles of gas are present? Okay, we already solved that. And now the sample has a mass of 0.525 grams, and we need to identify what it is. So how do we do this? Okay, well, the easiest way to just do this is to find the molar mass. We want to calculate the molar mass. So the molar mass, so MW, so that's the grams per mole, right? So we need to take the weight. So the weight is 0.525 and divided by N, so the number of moles. So here, so equals 70.9. Okay, so now we have the molar mass. So the molar mass is 70.9 grams per mole. Okay, so we look at the periodic table and see if there's anything that looks like 79. Okay, well, there's nothing, so it looks like we've messed up, but we haven't. The important thing to know is that all of these elements, see these elements, so exist as diatomic molecules. So these are what are called diatomic molecules because the molecules are the element too, okay? So this is the molar mass of the molecule. We need to find the molar mass of the element. So to do that, we divide this by 2. So dividing by 2, we get 35.5. Now let's see if there's an element like that. Oh, great, chlorine, 35.45. So the answer is that the sample is Cl2. Okay? Does anyone have any questions? If not, we can take a 10-minute break.